Hello, it's Dave Giles here for the next lesson of Cambridge International Education IGCSE Physics, and today we are looking at circular motion. And by the end of today's lesson, I'll only describe how objects travel in a circle and describe factors affecting circular motion. So to start us off, for the first learning objective, describing how objects travel in a circle, we're going to redefine some key terms and points from previous lessons. So I'll give you a few seconds, you can pause this, try it yourself. Okay, so the first one, define velocity. It's speed in a given direction. You could also have rate of change of displacement, but I'm going to stick with this definition for now. And definition of acceleration is the rate of change of velocity. Okay, so velocity has got direction, so acceleration must also have direction, and it's a vector quantity. Look at your first definition. If an object is accelerating, what could you change about the way it moves? There's two possible things. The most obvious one is the speed or direction. Now, I could have summarized that with velocity because that takes in both, but I've put both on here, speed or direction. Does the velocity of a person traveling when they walk around a corner traveling 3 meters per second change? Well, the answer is yes. Speed's constant, 3 meters per second, but the direction is changing, so therefore the velocity is changing, which is the answer to question 5. As direction changes, the velocity is also changing. And that's all links into today's lesson on circular motion. So here, this something you might not use depending on which country you're from, but it's a conker, quite common in England, being spun around on a piece of string. What shape path is the conker moving? Well, add an arrow to show the direction which the conker is moving at this instant. So it's currently moving this way. And what is the hand doing to the string? Add an arrow to show this. So that's providing an inward force. So this is the direction of the motion at that particular instant. And this is the tension in the string caused by the man or the person holding the string and spinning it around. So let's have a look here. This is the different path of the conker. And each of these blue balls here represents a different part of its path. And if you let go of any of these points, the black arrow shows which direction the conker would move off at. And it's 90 degrees to the string. So wherever it is, if I cut the string here, it will travel off at 90 degrees to the string in this direction. So this is the current displacement at that exact moment in time. But you can see the direction is constantly changing. So speed is constant, but direction is constantly changing. So velocity is constantly changing, which also means it is accelerating. So answer that question, yes, it is. Yes, because the velocity is changing, acceleration is towards the center. So it's always accelerating towards the center of the string. And you might think it looks like it's accelerating in a different direction, but don't forget the tension is inwards. Okay, so the tension is inwards. And if we go back to previous learning, F equals ma, or force is mass times acceleration. If the force is towards the center, which it is, then therefore it's accelerating towards the center as well. So let's have a look at why it moves in a circle. Well, it's because of the centripetal force, which is what we just mentioned earlier, the force being towards the center, which is why it's always accelerating towards the center. So the force is acting inwards, pulling the bung in, or conker, whatever object is it's being spun around. So how can we increase centripetal force? Now I'm going to show you a formula which you do not need to know at IGCSE. You do at A level, but you don't need to remember this formula at IGCSE. However, it is useful in describing how we can increase centripetal force. So F is mass times velocity squared over R. So the obvious thing is we increase the mass of the object, we can increase the velocity of the object, or we can reduce the radius of the object. Now, of those things, the velocity will have the biggest effect because if we double the velocity and F is proportional to v squared, that means if we double the velocity, then the force is times 4. However, you don't really need to know that, but you do need to know these key bullet points here in blue. So I'll put some questions on there. I'll let you pause it, work your way through them yourself, and I'll put the answer on in a few seconds. Just a note, the last question is actually a past paper question from an A-level exam. Okay, and I'll put the answer on now. Okay, hope you did well there. So now we'll do a few multiple choice questions where I will talk through the answers. So these are all from paper 2. A car is driven around a bend in the road at a constant speed. What's the direction of the resultant force on the car when it is going around the bend? Okay, so we know the force is at 90 degrees to the direction of the motion. So if let's have a look through our options here, we'll start at A. Parallel to the motion and in the same direction as the motion, no. Parallel to the motion and in the opposite direction, again, no, it's not parallel. Perpendicular, okay, that's a good start. To the motion and towards the inside, well, we know if it's going this way, then it's going to be inside, so it looks like the answer is C, but we'll double check with D. Perpendicular to the motion and towards the outside of the bend, no. So the resultant force is inwards, so perpendicular to the motion at 90 degrees. Next question. A planet orbits a star at a constant speed in a circular orbit, sorry. Which of these statements below around the force needed to maintain this motion is correct? Again, we'll work through it. We'll start from the top. No force is required to maintain the motion. That's just false. We need a force for motion, for circular motion. The force acts radially away from the center of the circle. Well, we know acts towards, so it's not that. The force in the same direction as the planet's motion. No, it's at 90 degrees. The force is direct to the center of the circular orbit. Yes, it is that one. Next question. The diagram shows a satellite that is moving at a uniform rate in a circular orbit around the Earth. Which statement describes the motion of the satellite? I'll start from the bottom. It's not accelerating, but its velocity is changing. Well, if its velocity is changing, it is accelerating, so that's false. It is not accelerating, but its speed is changing. That is also false. If speed's changing, yeah, accelerating or decelerating, depending on which way. It is accelerating because its velocity is changing. Yes, that is true, but we'll double check the last one. It is accelerating because its speed is changing. Now, its speed is changing. So, no, sorry, its speed is constant, but that is not why it is accelerating, okay? It's accelerating because its velocity is changing, because its direction is changing. So the answer is B. Okay. And that's it for today's lesson. So the next lesson will be on momentum, which again, I will be uploading fairly soon. Thank you very much, everyone, and I'll see you in the next lesson. Thank you and goodbye.